Hi everybody, welcome to my 10th axial bar video. In this video I'm going to be talking about what it means to be statically indeterminate, and then I'm going to go through a bunch of examples of problems I've seen that are statically indeterminate, and I'm going to show you how to solve them. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. So the definition of a statically indeterminate beam, or axial bar, or torsional bar, or anything that's statistically indeterminate, is when you don't have enough equations of equilibrium to solve for the internal forces. Okay, so I'm going to work through a few examples that I have prepared here. And I'm not going to go through and solve an example for each one, but I'm just going to show you the general method of solving each of these situations. So the first one that I think of is, and is also the most common, I call a bar between two walls. All right, and that essentially looks like this. All right, you have a wall, a bar, another wall. Okay, and then just supposedly you'd have a force there, P. All right, and now in this situation you can imagine we're gonna have a reaction here and a reaction here. So when we do equilibrium of the overall thing, we're gonna have P and then R, let's call A, and RB. And when we go to find the internal forces, we're also going to have everything in terms of the outside forces and, N1, N2 you could call it. But it's going to turn out that you're not going to have enough equations in equilibrium to solve for those unknowns. And I'll get to the specifics of that in my next few videos. I'll work through these examples. I just want to give you an overview here. So how are we going to go about solving this problem then? All right, we need to rely on another source, and that source, that key, if you will, is going to be displacement. All right, we know that displacement is the N, the internal normal force, L over EA. All right, and this normal force here, well, that's what we want to solve for. So if we have a condition where it's statistically indeterminate, we can find an equation of equilibrium, and we can find an equation of displacements, and we can solve those two equations simultaneously to obtain the normal forces. Okay, so in this situation here, the displacement you can find just by taking a look at this specific scenario. So you know that anywhere something is fixed to, like a wall, there's going to be no displacement. So the displacement here and the displacement here is going to be 0. So that means if it gets pushed to the left here on this side, that means it must get pulled to the right on this side, or there must be some sort of way that even if it's stretching, it's getting pushed back before it gets there. So we can write the sum of the displacements equals 0. Okay? I'll get into this more in my next video. All right, the second sort of problem that I've seen around is some sort of lever with, I could call them bars or ropes. Let's just call them bars. Okay, and an example I could think of would be like this here. All right, you got some sort of lever arm here, and it's attached to the ceiling by two of these supports, and you're pulling down it here with some load, P. So if we take a look at this one, why is it statistically indeterminate? Well, if we recall back to our definition of statistical indeterminacy, when you don't have enough equations to find the internal forces by looking at equilibrium equations alone. So let's apply the two equilibrium equations we know, sum of forces and sum of moments. All right, so you can imagine the sum of moments around this point, we're going to have this force in there, this force in there, and this force in there. Okay, one equation, we got the two normal forces. Okay, so if we could find another equation, let's take a look at the forces. I have P, the normal force in here, the normal force in here. But wait, we also have the reaction here. And that was not in our moments because we took moments about this point, and a force applied to it at the point of rotation contributes no moment. All right, so we're going to have two equations, three unknowns. So this is statistically indeterminate. Again, we need to rely on displacement. Okay, there's a few other ways you can set up this bar. You could have it like this, possibly with the little bit of a fulcrum happening there, and then you could have the same sort of situation like this. All right, this is just a few examples I've seen around, and they all can be solved in a similar way. So, since we don't have enough information from the equilibrium equations, we're going to go to displacements. So displacements for this one, let's try to keep the displacement information all on this side here, is basically you're relating if this thing moves, how much does each point move, you know? So if we would draw this beam here before it undergoes any sort of rotation, like so, then we can imagine after it's been pulled, it's going to rest in some sort of deformed state like this. Okay? So that would make it so that the displacement of the one would be here, and the displacement of the other would be here. Alright? So let's just give this like a distance here. Now let's say 2, 2, 1. We'll call this delta 1, delta 2, just for the sake of this example. And then we can work through similar triangles. Alright? We can say that the ratio of this length to this length is the same as the ratio of this to that. So you could say delta, oh sorry, I'll put it over here. Delta 1 over 2 is equal to delta 2 over 2 plus 2 up to here, 4. Alright, and that's the displacement equation. We plug in this, and then we have another equation that has normal forces in it, allowing us to solve an equilibrium equation. Alright, the next example that I've seen a lot is some sort of composite bar or composite slab or something. So it's basically like a can, like such, and then inside there will be like a core of another material. Alright, so I'm going to draw it like this. Alright, so this is another material here. So this would be potentially E1, E2. Alright, and this one's statistically indeterminate because if we would apply a load on the top here, P, we can imagine a free body diagram of two forces pushing back. The force from the piece E1 and the force from the piece E2. Alright, and now you can't do anything about this. You can't really take moments. You can only really do forces. We're going to have two unknowns. But the displacement in this case is quite easy. You can imagine if you push on this top piece here, they're both going to displace down the same amount. Alright, there's no way that the middle piece of material is going to be like, way lower than this other piece, or somehow this piece is going to stick up. If you have like a flat plate and you're pushing down on that flat plate, the whole thing is going to displace evenly. So then you can say delta 1 equals delta 2. And then again, sub in your equation here for the forces, and then solve it simultaneously with the other one, the equilibrium. I call this one, some sort of composite bar. There we go. The fourth example that I've seen around, either in textbooks or quizzes or anything like that is 3 cables in tension. Alright, so basically the situation kind of looks like this. 3 sort of cables. They might have similar or dissimilar properties, and you have some sort of bar or weight, and then you're pulling down on this with a force. Alright, and we can see why this is statistically indeterminate, because we have 3 forces pulling up, 1 force pulling down. We can do some of the forces, some of the moments, but we're still not going to have enough information because that's only 2 equations and we have 3 unknowns. So then again we have to go back to displacement, and we can say, if we call this 1, 2, 3, of course when you pull down, they're all going to be stretched equally in terms of the physical displacements. So we can say delta 1 is delta 2 is delta 3, and then again sub in this equation and solve for forces, moments, and displacement simultaneously to get your normal forces. Alright, and then the final sort of category, I guess you could say, of statistically indeterminate problems I've seen in this course are the ones that have more of like a complex displacement. Alright, so it's not actually like complex, it's not like as straightforward as, a simple geometric relationship. Alright, so the one that comes to mind for me, and the one that I'm going to be working through in a later video, goes like this. You have a chunk of plastic, And it's got like some sort of lid on top like this. And then it also has some screws like such, and they all have, you know, threads. And then on top you have some nuts like this. Now the question is, you tighten these things, what is the final normal force in here, the final stress in here or something, all right? So basically what happens is when you tighten these bolts, this plate moves down, but as it's moving down, it's also being pushed up by this piece of, like, let's just call it plastic here. So the amount that these nuts turn down in one pull is not going to be the displacement, because this is pushing back up, thereby stretching those threaded pieces of rod here. So the best way to visualize this one is to draw a very good before and after picture. So this would be before, and I like to think of this one in two stages. You tighten the bolts, it goes down, pretend the plastic is in there, and then the plastic pushes it back up a little ways. So this is called this one, it pushes it all the way down to some position here. Alright, let's call that 2. And then the plastic pushes it up to some final position. Let's just make this a little more obvious here. 3. Okay. So the displacement, the final displacement of the plastic and the final displacement of the bolts are basically these distances here. So I'll measure relative to the bottom of this plate. You can pick any point on that plate, but it's essentially the same. Alright, if we measured it all from the top to the top to the top, it would be the same. Okay, I measure from the bottom for no particular reason. So the amount that the plate moves down and then back up. So you can imagine this is the point here where those threaded columns or threaded rods start to be under some sort of tension, if you will. They start to displace. So the displacement of the rods is this bit here. Displacement rods, let's just call it. Alright, now I said it's 3 steps, so the plastic initially gets compressed down to here, then it goes up to here, so its final resting place is here. So that means from the initial position to its final resting position, the plastic has moved a displacement this much. Alright, and then this overall bit here is the amount by which I screwed the nuts down on the top. So it's probably going to give you some sort of pitch or something, and then a number of turns, where they'll say you move it 5 millimeters down, and then from there it gets a displacement. Anyway, you're going to know like a number here, alright? So I'll call this, like, I don't know, let's give it a variable A, alright? And then very simply we can say A equals 2 delta plastic plus delta of the rods. And then you do the same thing, you put NL over AE in there, and then you solve with your equilibrium equations. So these are the 5 sort of categories of statistically indeterminate problems. So just in review, a statistically indeterminate problem is a problem where you don't have enough information by looking only at the forces and equilibrium and moment equations. You need extra information to solve for the internal normal forces, and that extra bit of information you need is the displacement. Of course, there's a bunch of different situations. Each situation requires a different method of analyzing the displacement. So on a bar in between 2 walls, you know that the walls don't move, so the displacement between here and here has got to be 0. Lever with bars, by looking at the shape of the original conformation and then the shape of the final configuration, you can use similar triangles to find a relationship. A composite bar, anything composite chunk, you know that when it gets compressed, the deltas equal each other through cables in tension, kind of the same situation. And of course, a more complex displacement, like this example here, which has actually some sort of relationship between the two, which requires you to draw a really neat, accurate picture to get an idea of what's going on. Alright, hope this video helped you guys a bit out on this statistical indeterminate stuff. In the next few videos, I'm going to work through some of the very examples you see here. Alright, I'll see you around.